Could that start life? Could that create life? Our solar system. We've been studying our solar system. It's the only place in the universe we can get to. Not even with people on the spacecraft, but even with spacecraft getting there within our lifetimes. At the technology right now, we're going to talk about at least tens of thousands of years to get to the nearest stars. Let's go over some things that you've learned and set up chapter 9, the leftovers. So you know, there's some weird idea piecing together the evidence about the Big Bang, where the universe started out of nothing. Somehow, lots of good questions there. You know how long ago? 14 billion years ago. Our solar system, 4.6 billion years ago. A lot happened before our solar system came into being. So with our universe starting, as best the evidence tells us, let's go with 14 billion years ago. Within the first billion years, started to clump up. You create atoms, a lot of hydrogen and helium, and you get these clouds, right? But the clouds so big we can't imagine them. And then they clump up and we get these groups of galaxies, islands of stars, right? And within that, stars started to form, right? And perhaps outside, but stars started to form. And it turns out, we can see in chapter 11 again, large stars will have a lot of gravity and they'll squeeze and they'll go through their life cycles very quickly. Now we're talking 14 billion years start a universe, 13 billion years galaxies, early stars. They go through their life cycles quickly. They build up atoms, other atoms besides hydrogen and helium. Right? They go through their life and they explode. 13 billion years ago. We got 4.6 billion for our solar system. Our solar system's not around yet. But other stars form, and the big ones squeeze together to create bigger atoms, explode, and that gas comes together into a new generation of stars. And then eventually, out of that gas, the leftovers of that explosion, the gas comes together and forms our solar system, right? So we can think about this stuff now. Having studied initially going through this, it's a lot of information and it's confusing, but the more you piece it together, you get a sense. You step out into the sky and you can think about at least some of these ideas and how they're connected. And so our solar system, it's the only place we can go to with spacecraft. I mean, you could send people you don't like out there, I suppose. But we know that we can go to moon and come back. That's doable, been done, right? Apollo, and then we got Artemis, right? And so up and back in a week. Mars, maybe. Venus is closer when I go there. It's not as friendly. It's a little more friendly over here in Mars. I think we'll go over to Mars. You know, maybe we can try that. But that's a huge challenge. Certainly as of yet, not there. So we send spacecraft out here. Start with the spacecraft of the 50s and 60s and the late 60s and 70s, Apollo, and you get to late 70s, 80s, Voyager going way out here. And then the spacecraft get better, the technology get better, the computers get better. And we got in the 90s, right? We have 89 leaving here, getting over here. Galileo, the first spacecraft to go into orbit around an outer planet, taking about 5 years to get there. Right? like that, hang out there for a while. What? 9 years orbiting. You don't want it to run into Europa, so you dive it into Jupiter. Take data. So you head up. Well, while that's going on, you send another one, fly by here, say hello, Cassini, right? Leaving in 1997, finishing its mission 20 years later in 2017, and then diving into Saturn. And then we've got Juno up here, studying in more detail. And so this is human history, starting looking up and wondering, and now going, but only in our solar system. And we wondered about things from antiquity. How did life start? I don't know. Did people even wonder that? What are those dots in the sky? What's our role? What are those wandering things doing? Do they rule us? Who's messing up my life and things don't always go the way I want it to? Who can I blame? So we look up and we wonder about these things. And now we're looking for life. We're going out and we're looking for life. Mars, Europa, one of the moons here, Enceladus, Titan. We're looking for life here because we can't go to other places, but we can find planets around other stars now as of 1996, right? So as of 1996, we've got planets in this neighborhood, and if there's a lot of planets here, then they're probably here. And they're probably here. And it's not just planets, it could be moons. So life. It's not the only thing that we're interested in astronomy. We develop technology that ends up in our hospitals and all kinds of good stuff. So exploration leads to surprising discoveries, and we've been exploring. It's hard to get away from that question of life. How do you start life? So it's kind of fascinating. Water. Where does the water come from? Metal, different metals. Where do they come from? What's a shooting star? Different sizes, helping us learn about Earth and ourselves. So we're going to talk about the leftovers. You know, the memory aid. My very excellent mother actually just sent us 9 pizzas and Cokes. These little bits. See, we talked about worlds, and we said that these worlds, if they changed, and we know they all formed at the same time, 4.6 billion years ago, but if they changed, then we call it a new surface. It's resurfaced, it's changed, but it formed in terms of age. But if it hasn't changed on smaller worlds, we call it an old surface. Changes happen with chemical processes, etc. Well, what if you get something smaller? Is that going to change much? Depends on what it's made of, right? Well, what's interesting about asteroids and comets, asteroid chunks that haven't changed since the formation of our solar system 4.6 billion years ago. And so there's a lot of information in here. We've landed on asteroids, we've flown by asteroids, we've crashed into a comet and sent it up, deep impact. And we study this. Who knows what we learn? We explore. That's part of being human. We explore. And the cost is actually very small. The dividends are huge. So we study. Now leftovers, chapter 9. We're about to finish this, except we won't be done, will we? Because we won't have studied sun. So we'll go on to sun and stars and tie this all together as we do. And think about, where does carbon come from? Where does oxygen come from? Where does iron? How come Mars is the red planet? Well, kind of orange really, isn't it? Or rust colored? Because it is rust, right? Iron, oxide. Where'd the iron and the oxygen come from? Big Mama. So it ties together, and it's kind of cool. We know about the widths and distances, making making the difference that it does. We know that when we look up with the widths and distance, we look up at moon, and it looks the same size as sun. In fact, moon can cover it, right? In a solar eclipse on a new moon. Occasionally does that. Why? Because sun is 100 times wider than Earth, 109, 400 times wider than moon, yet it's 400 times farther away, so it looks smaller. Just a little review. But wait, what would it look like for Mercury? I mean, you're a third as far away. So sun would be 3 times wider. 3 times wider seen from Mercury. Talking about sunburn. Whereas from Mars, it's going to be smaller. Looking at sun from Jupiter, 1 AU, and then from here to here, 4 AUs, so my drawing's not right, way out there, another 4 AUs, another 10 AU, another 10 AU, way out there, and sun starts to become smaller and smaller, and you get rather chilly. So we can start to summarize these ideas, pull all of this stuff together, including looking up and wondering. And we're going to do that, and we're going to see the important role of the leftovers: asteroids, comets, and meteoroids. So let's embark on that.